Hello students, welcome back. I hope that you are following this lecture from the starting. We started with alkyl halides. We discussed about how they are formed and what are the different ways of classifying the alkyl halides and how to name them. And then we also discussed about the physical as well as the chemical properties of alkyl halides. So now we are going to discuss about aryl halides. So what are aryl halides? How do they differ from alkyl halides? So let's start the journey of aryl halides now. So students, we are done with the alkyl halides or haloalkenes. So we are moving to the next part of this chapter, that is aryl halides or haloarenes. So let's see how this aryl halides are different from alkyl halides and where does this difference comes from. Aryl halides are also known as haloarenes are the compounds which contain at least one aromatic ring. They contain at least one aromatic ring, and the halogen derivatives of aromatic compounds are of two types. There are two types. One is aryl halides, another is aryalkyl halides. So first we will see about aryl halides. So in aryl halides, the halogen atom is directly linked to the carbon of the benzene nucleus. You can see here the halogen atom is directly linked to the carbon of benzene nucleus. These are known as aryl halides. And the second type is aryalkyl halides. That is, it contains both alkyl as well as aryl groups. So in these compounds, halogen is linked to the carbon atom of the side chain, which is linked to the benzene nucleus. So here the iodine is not directly linked to the carbon of benzene, but it is linked to the carbon of side chain, which is in fact linked to the benzene nucleus. So which are known as aryalkyl halides. So we have two types of aryl halides. One is aryl halides, other is aryalkyl halides. So let's get into the properties of these aryl halides. First is the boiling point and melting points. So the boiling points of monohalogen derivatives of benzene follows this order. So we know that the boiling point depends upon the intermolecular attractions that are van der Waals forces, dipole-dipole interactions. So which depends on the molecular weight as well as surface area. So the boiling points of the monohalogen derivatives like iodobenzene, bromobenzene, chlorobenzene, if you see, the iodo one is going to have more boiling point because of more molecular weight, and bromine is going to have higher than chlorobenzene. Okay, so if you see, the boiling points of isomeric dihalobenzenes are nearly same. So if I take the dihalobenzenes, like let's say diiodobenzene, so one iodine, another iodine, so these are ortho. So they may be para also, like if I take this one, so one iodine is here, other iodine is at meta position. Other isomer of this diiodobenzene is this one. So these three are the isomeric dihalobenzenes, So the boiling points of these are nearly same, right? Because they are going to have same molecular weight and they are going to have approximately same surface area they are going to occupy. So the boiling points are not going to vary much. But however, their melting points are quite different. They show some considerable difference in their melting points. So let's see the reason for that. So the melting point of the para isomer is generally 70 to 100 degrees centigrade, 100 degrees more than the melting points of ortho and para. So these two are having almost same, but the para is having more than, like it will be 70 to 100 degrees more than the ortho and meta isomers. So what's the reason for that? Why the meta one is going to have more melting point, right? So we'll get the answer to this question in my next slide. So the boiling point and melting points of these three, if you see, the boiling points are nearly same. They're not exactly, but they're approximately same. But if you see the melting points, so the para one is having more than, it is 250, it is 325. So it will be more around 76, exactly 76 more, right? So why does this large difference comes? But these ortho and meta are having nearly same. are having nearly same. They have only difference of 7. So, but here the difference is 75. So, what is the reason for that? The reason is simple. You know that the melting point is depends upon how the molecules are arranged in their crystal lattice, right? How closely they are packed and how effectively they are packed. So, the melting point of para-isomer is due to its symmetry. So, if it is symmetry, if they are symmetrical, then it's easy for it to have a more close packed structure. So, that symmetry which leads to more close and packed structure in the crystal lattice. So, that's why since it is more closely packed, so you need to supply more energy to get them apart. So, that's why its melting point is considerably higher than the melting point of the corresponding ortho and meta isomers. So, let us see the solubility. So, how the solubility of aryl halides varies. So, whether they are soluble in water or not, let us see. So, haloarenes are soluble in water, they are insoluble in water, they are not soluble, but they are soluble in organic solvents like haloalkenes, right. So, what is the reason for the insolubility of haloarenes in water? It is because they cannot form hydrogen bonds with the water molecules, right. So, due to their inability to form hydrogen bonds with water molecules, the haloarenes are insoluble in water. Okay, let us proceed then. Yeah, so now let us see the reactivity. How the reactivity of aryl halides is different from the reactivity of alkyl halides, and what are the reason for that? So, if you see, the aryl halides are much less reactive towards the nucleophilic substitution reactions. They are much less reactive as compared to the haloalkenes. So, what is the reason for their less reactivity? So, these are the three reasons, the primary reasons. One is the withdrawal of electrons by benzene and stabilization by resonance, and second is the different hybrid states of carbon atom which is attached to the benzene ring, and third is the polarity of the CX bond. So, these three are the reasons for the low reactivity of aryl halides as compared to the alkyl halides. So, let us go one by one. Let us look at each of them in depth. So, the first thing is the withdrawal of electrons by benzene. So, you can see here the halogen atom is having a 3 lone pair of electrons on its head, right. So, the 3 lone pair of electrons, so these lone pair of electrons are in conjugation with the double bond. So, this halogen donates this lone pair of electron and we will get a set of resonance structures or canonical structures. So, yeah, you can see when this lone pair comes in, this double bond comes here. So, you will get the 2, 3, 4 are the resonance structures. So, the hybrid you can write the hybrid. So, thus the exact halobenzene is the resonance hybrid of all the following structures, right. So, none of them is correct enough to represent the property of the old one. So, we are going to combine all these structures and will form a hybrid, and that hybrid is going to explain the properties effectively, other than not all of them. So, each one explains partially, but the hybrid is going to explain the properties completely. So, we call that as resonance hybrid. So, if you see the contributing structures, the second one, the 2, 3 and 4, if you see these 3, here there is a double bond and double bond, right. So, before it was a single bond, but now it is a double bond. So, the bond it is not exactly single and it is not exactly double. So, it is in between the single and double bond. So, that is known as partial double bond character, right, the partial double bond character. So, we think that the carbon halogen bond length is the single bond length, but that is in fact less than the single bond length, and that is more than the double bond length. So, it is intermediate between the single and double bonds. So, that partial double bond character you can understand by the resonance structures 2, 3 and 4. So, as a result, what happens is the CX bond in halobenzene is shorter, right. is shorter and hence it is stronger as compared to that in alkyl halides. Okay. So there is a difference in the CX bond length and bond energies of alkyl and aryl halides. This is one of the primary reason that why they are not so reactive, because of this bond is not easily, you cannot break this bond easily because of the partial double bond character. And the second is the different hybrid states of carbon atom. Okay. So if you can observe the carbon of alkyl halide to the carbon of aryl halides, so the difference you can find is in alkyl it is sp3 hybridization the carbon, but in aryl it is sp2. So this hybridization is also making the reactivity different for both of them. So the sp2 hybrid orbital is smaller in size due to the greater s character, right? Here the percentage of s character is how much? 1/3, it is 33%, but here it is 25%. So because of high s character, the sp2 hybrid orbital is smaller in size. So because of that, the bond in haloarenes, that is a carbon halogen bond in haloarenes, is smaller and is cleaved with difficulty. This is the other reason. And the third one is the polarity of the CX bond. So the CX bond in haloalkanes is more polar, but here it is not that much polar, So if greater is the polarity of the bond, then more is the reactivity. So in haloarenes the polarity is less, so that's why it is less reactive. So these are all the reasons for why the haloarenes are less reactive towards the nucleophilic substitution reactions as compared to the alkyl halides, right? So this is all about the difference in the reactivity and the properties. So in our next video, we are going to discuss about the different chemical reactions shown by aryl halides. While studying this chapter, if you get any doubts, you can post it for free on askIITians.com. How? First, open the website, and if you see at the top right, you will see a discussion board. So simply click on that. It will take you to the next screen. Yeah. In the next screen, you will see the Ask Experts, a separate section on the right hand side. So select a relevant category for your question and simply post your question here. We experts at askIITians will provide answers to your questions within 24 to 48 hours. So students, in this particular part, we discussed about what is in aryl halide. We also see how the solubility and boiling point of aryl halide varies. And then we also discussed about the reasons which are responsible for difference in the reactivity of both alkyl and aryl halides. So now in our next part, we are going to discuss about the chemical reactions of aryl halides. So keep watching for my next part.